The last aspect of the phases, solid, liquid, gas, are phase diagrams. And phase diagrams is a graphical representation of how the phase changes from one to the other and what temperature, what pressure is required for that. So again, just a little review about the phase changes. We talked about this, of course, at the beginning of the chapter, but here is another representation. So here's temperature. And I like this one a little bit better than the one we had before because this one also shows some energy considerations here. The one we had previously does not show the energy, okay, in there. So if the temperature is increasing, then you have melting going on, which shows right here. So melting goes from solid to liquid. And then as the temperature increases, the liquid goes to gas, which is called vaporization or evaporation. This long arrow over here shows that solid is going right to gas, which means it is sublimation. These three over here, of course, as you can see, are solid, liquid, gas, the phases, and then the blue lines show you all the reverse processes, the freezing, the condensation, deposition. And so all of these are nice little energy and graphical representation of the phase changes that go on. This was the triangle I gave you before, and now I've actually drawn it out for you. So hopefully you've drawn a similar one for yourself when I gave it to you before. But these are all the phase changes that you need to know. So there is something called a heating curve, okay? And the heating curves shows you how the phase changes with temperature, okay? So a heating graph shows how the temperature changes of a substance. So for example, if you start giving heat to any substance that's a solid, it's going to start changing into a liquid, okay? But look at over here, as over the time, even though you're heating a substance, over time the phase does not change, okay? It remains the same. Then the phase changes to liquid, okay, as the temperature increases. And then as the temperature, you're still applying temperature, but then nothing happens again. There is a plateau, and then C and D is a plateau, and after that the liquid changes into vapor. So in any kind of a heating curve, it's not really a direct curve, okay, which means that you have these lines, in which case you can see the phase changing, but then you also have these plateaus where nothing is happening, okay, but that's not true, okay, there is something happening in there. So the phase changes are very clear, where you have the melting going on or where you have evaporation going on. That's very clear. The plateaus actually indicate that you have the energy that is being supplied, but it's used for something different other than changing the phase. And something that is different is actually intermolecular forces. So wherever you see plateaus, it's actually the energy that is used to break the intermolecular forces, where you have dynamic equilibrium going on, which means heat is being absorbed, but it's not being used to actually change anything. Whatever you're converting from one phase to another is coming right back, okay? Until that threshold is crossed, you will not see a phase change, okay? And so there is some amount of energy that is used up in breaking those intermolecular forces. So sometimes, you know, when they say a washed pot never boils, and that is because you're watching and you're looking at like, okay, it should boil right now because you've been supplying it with enough energy, and it seems like it should boil, but it's not boiling. And that is actually the intermolecular forces that are breaking apart. So you need that energy to do that in order for the phase to change. So phase diagrams in generally are separated by lines, and they represent equilibrium between different phases. And you can see that clearly as I go on to the next slide. There are a few things that I need to mention to you because you're going to see these words in the charts as we read them. One is called critical temperature, and the critical temperature is the temperature above which a gas cannot be liquefied. So you can apply as much pressure as you want, but unless you lower the temperature, the gas is not going to condense, okay? So which means that there is a specific temperature at which you cannot liquefy the gas, all right? So which means it will not condense. Then there's something called critical pressure, and the critical pressure is the pressure that must be applied to liquefy a gas. So which means that these two actually are related to each other, okay, in a way. So at a certain temperature, you should be able to apply a certain amount of pressure that can liquefy a gas, but then above that critical temperature, you cannot liquefy a gas, all right? And then there's something called a supercritical fluid, and which is a very interesting aspect of all of the different substances, is the supercritical fluid exists above TC and PC, which means critical temperature and critical pressure. And this is a very unique phase for any substance, okay? And in this kind of a temperature and pressure, which is a very critical type of a temperature and pressure, a gas starts behaving like a liquid and the liquid starts behaving like a gas, and both of them are kind of interchangeable. You cannot tell the difference. Usually gas molecules are all spread out and they do whatever they want, but a supercritical fluid is still a gas, but it behaves like a fluid. It behaves like a liquid. Okay, so it's really a very interesting phase of substances. So here's a phase diagram. We'll start with water, and because this is Gen Chem and not physical chemistry, we don't really have a very good graph here, okay, which means that the temperature scale and the pressure scale are not all graded for you. Okay, so there is the normal pressure, which is 1 degree, and then the temperature here that is given to you is a 0 and 100, and that's it. Okay, so it's not even up to scale as far as that is concerned. But what you really should see from this diagram is what a phase diagram looks like. Okay, so in a phase diagram, you will have pressure and temperature scales. You will also have these 3 different phases. Okay, so this is something that you actually do experimentally and you figure it out. Okay, and that's how you draw this graph. So you have the 3 phases, which is the solid, liquid, and gas, and of course the gas will occur at a higher temperature, okay, and at a low pressure. At high pressure, you will have solid. At high pressure, you will have liquid, okay, and then at low temperature, you will have solid. Okay, that's what this phase indicates. So that's what a phase diagram would look like. And usually the questions that are asked of you would be, well, if the pressure is 2 atmospheres and the temperature is 100, then what phase do you expect? Well, at 2 atmosphere, which if we just take the double of this, which would be over here, and the temperature is about 100, then we would expect water to be a liquid, okay, at those 2 conditions, all right? And so that is how you would read a phase diagram. They're fairly easy to read and decipher. There's nothing much about this. All of these different lines here, these are the equilibrium points, okay, or the equilibrium areas. So for example, the A and B is the equilibrium between solid and liquid. A and C is the curve for gas to liquid equilibrium. So they just indicate equilibrium. So it's a nice way to show the change in the phase also that is occurring. And here is the phase diagram for carbon dioxide, which is a gas. And at STP, carbon dioxide is never going to be a liquid. Okay, and it shows that over here also. Now the temperature scale is not very good, okay, over here. So if the critical point, which is given to us over here, we can presume right here that this is going to be 31 degrees Celsius. Okay, so 31 degrees Celsius is like a nice warm day. Okay, and so if that is how we're going to read our graph, then at normal temperature and pressure, which is 25 degrees Celsius, which would be over here, and then 1 atmosphere, then you would have gas, okay, which is the normal gas phase, okay? And then at 25 and 1 atmosphere, you can have a solid. Your temperature is a little bit low, okay, but you can have a solid, but never a liquid. Okay, so the liquid at 1 pressure, at 1 atmospheric pressure is never really reached, which means that at normal pressure, you will never have a liquid carbon dioxide, which means that the carbon dioxide will go straight from solid to gas, which means that sublimation will occur. And you might have heard of carbon dioxide as a solid, as in dry ice. Okay, so we call it dry ice because it looks like ice. It is a solid, but it's called dry ice because as soon as you keep it outside at normal pressure and normal temperature, it's going to be dry ice at -78. But if you bring it to normal temperature, which is around 25, it's going to go to gas, okay, at that temperature. So it goes from solid to gas right away, and so that means it is subliming, okay, at that point. But it doesn't wet anything because it's not like water, okay. So it goes straight into a gas phase and not into a liquid phase, which is why it never wets anything. But anyhow, that's the interesting thing about carbon dioxide. And then at critical point, the gas starts to behave like a liquid. Okay, and that's one other thing about carbon dioxide that's very interesting, is the critical point of carbon dioxide. There are some applications of carbon dioxide that are very interesting that come out of this phase diagram, because once you know the properties of a substance at different temperature and pressure, you can find applications for it, okay, and use it to your benefit, okay, in some ways. And so we'll talk about that in class. Anyhow, that's what this is. And then here is the triple point. We didn't talk about triple point before, but anyhow, this is the triple point. At triple point, all the three phases can occur simultaneously. Here is a phase diagram for sulfur. Again, these are just coming out of textbooks, and therefore the scales are not very good for this. And again, it's not PChem, and therefore the scales are not very good. However, it is interesting to see that in case of sulfur, you have something else going on, okay, and that is the allotropes, because in case of sulfur, there are two kinds of allotropes, a rhombic and a monoclinic structure. And so because of that, you see all of these different things too. So at different temperature and pressure, you can have these two different structures for sulfur. And then of course there's the gas and the liquid also, okay. And so the phase diagrams are very interesting, and so you can control how you want a substance to behave according to the temperature and pressure of the substance. So here is an example, a solved problem for reading a phase diagram. So here is a question. Using the phase diagram that's given over here, determine the normal boiling point and melting point of a substance. The normal boiling point and melting point, of course, would be at 1 atmosphere. Determine the physical state of a substance at 2 atmosphere and 110, and then determine the pressure and temperature that correspond to the triple point. Okay, and so it's phase diagrams, as I said to you, not very hard. Okay, so the thing that is really critical for you to do in phase diagram is draw lines. Okay, so that's what we're going to do with this. So to determine the normal boiling point and melting point of a substance, you start drawing lines, and the first one we'll draw is a black one, and then we'll draw that at 1 atmospheric pressure, okay, which is right over here. So here is that line, okay. So for us, that's our atmospheric pressure. And so then our purple lines is going to answer the first question, which is the normal boiling point and melting point of a substance. And the melting point and boiling points are phase changes that are going on. Okay, and remember, this is the solid phase, this is the liquid, and this is the gas phase. Gas phase will occur at low temperature, okay, and and even in high temperature at low pressure. So this is all the gas phase, this is the solid phase. So for example, the purple lines here will show you then the two phase changes that are occurring. So the phase change is occurring right here between solid and liquid, and that is going to be the melting point of a substance. And going from liquid to a gas phase, that is going to be the boiling point of a substance. Okay, and so the boiling point turns out to be at about 200 degrees Celsius, and the melting point will come out to be at about 140 degrees Celsius. So that is how you would read this first part, okay, which is question number A. Question B, which is determine the physical state of a substance at 2 atmosphere and 110. So which means I'm going to draw another line. I'm going to draw blue lines for this one. And in this case, we'll start from 2 atmosphere and then at 110 and project it down to 110. And so where those two lines meet is actually at a solid phase. Okay, so which means that the compound would be, or whatever the substance is going to be in the solid state. And finally, determine the temperature pressure that correspond to the triple point of the substance. The triple point of the substance is right here. Okay, so now I'm going to have to draw another line to figure out what those lines are. Now my blue line is going right through it, so I may not have to draw a line from here, but I'm going to draw another line, which is going to be my green line, which will take me from this point to the pressure. So I already have the temperature as about 110, but my pressure is going to be out 0.8 atmosphere, okay, for this one. So that is how you read a phase diagram. You just have to sit with a ruler and draw lines and make sure that you're in the right phase, okay, and you're reading the right thing. So the key terms that I need you to know from all of this is, of course, the different phases of substances again, the critical words that I told you, the critical temperature and pressure, the triple points, and of course be able to decipher some of the phase diagrams that we talked about. And of course, I'll give you more.